Hey everyone, thanks for tuning into this discussion on pivots and their impact on solutions. We'll start as usual with a couple of warm up problems for you to consider. So I'd suggest just pausing here for a minute and seeing if you can do these problems. So take a minute, I'm going to come right back and we'll do the problems together. All right. So hopefully you took some time, you tried out those problems to reduce these two matrices. So these are just matrices; they're not anything that corresponds to a system of equations right now. Just matrices that we want to reduce to their equivalent reduced row echelon form. And that's the form where we have pivots that are taking on the value of 1, and all entries above and below a pivot are zeros. So what we'll do is we'll just take a couple of minutes to do these together. I'm going to cheat a little bit and I'm going to make use of Jonathan Foran's row reducer, mostly because I don't have pen input here, but also because I think it'll keep us a little bit more efficient and I will make less arithmetic mistakes. So I'm just going to type in the matrix. So give me a second to do that. And then we'll start with the row reduction process. So what we like here is we've got a 1 in the top left corner. That's going to be our first pivot. So we'd like to zero out the single entry here that's below it. And we're going to do that via our row replacement operation, which is indicated here in the applet by add. So we're going to replace row 2 with the original row 2. So one copy of row 2 here. And then we're going to add row 1 to it, but we're going to add -3 times row 1 to it. Again, -3 times the pivot. So -3 times 1 is -3, and -3 plus 3 is what's going to give us our 0. And so if we evaluate that, now we end up in a scenario where we have a bottom row that's equal to 0 in the first entry, 0 in the second entry, and 1 in the rightmost entry. This now, like if this were to correspond to a system, we would have identified that there are no solutions here because we have a pivot in the rightmost column. But since this is just a generic matrix that doesn't correspond to a system, let's go further and let's reduce it to its reduced row echelon form. We've got now a pivot in the top left corner. Our pivot in the second row is all the way here over in the rightmost column. And so what we'll do is we'll zero out the entry above that. So we're going to replace row 1 with the original row 1, but then just plus 1 copy of row 2, again, indicating that I can zero out this entry if I just add these two entries together. And so if I add row 1 and row 2, now I get this form. So pivot in the top left, zeros below it, no zeros, no rows above it, so nothing to worry about there. And pivot in the bottom right here, no rows below it, so nothing to worry about there, and a 0 above. And so there's the reduced row echelon form for that first matrix. Let's go ahead and just work through the second one. Just for extra practice, so I'm going to start by typing this in. There is a non-obvious start to this one, perhaps. We're used to maybe either already starting with a 1 in the pivot position or having an easy opportunity to just swap 2 rows and put a 1 in that pivot position, but that's not always the case. So here we are with our original matrix. There's any number of things that you can do here to perform your row reduction. There's not one method to get from start to finish. Sometimes it is just what you're seeing in that moment. And so what I'm seeing here is if I replace row 1 with row 1 plus row 3, 19 plus -18 is going to get me a 1 in that top left position, and I like that. We like having pivots that are 1s because they're easy to deal with, and so let's replace row 1 with row 1 plus row 3. Perfect. Now we can go through our usual row reduction procedure. I'm going to replace row 2 to get rid of this 6. So I'm going to start with row 2. I'm going to replace it with the original row 2 plus -6 times row 1. Again, that's the beauty of having a 1 in the pivot position, is it's much easier to choose our scalars. It's much more obvious what we need to work with. And so doing that row replacement operation zeroes out that second entry. We can do a similar thing here to zero out the lower left corner. I'm going to replace row 3 this time with the original row 3. And then if I add 18 times 1 here, would give us the cancellation we're looking for. So I'm going to add 18 times row 1 to that. And now we've got our first column in a nice form. We've got the 1 in the pivot position. We've got zeros below it. We'll move on now to the second row. We've got this -2 currently in the pivot position. Again, there's no nice row swap that we can do in order to put a 1 in that pivot position, but we might notice that all the entries in the second row are even, and so we can scale that row to get a 1 in our pivot position. So I'm going to scale this by -1/2. -1/2 times 2 is what's going to give me my 1, and so I have now a 1 in that pivot position. I've already got a 0 above the pivot, so we'll zero out the entry below it. We're going to use our row replacement operation for that. So we're going to replace row 3 with the original row 3 plus -6 times row 2. And again, -6, because -6 times 1 gives me -6. -6 plus 6 is what's going to give me that 0. And so there we are. Now we've got 1 in the top left as our pivot. That's the only non-zero entry in that column. In the second column, we've got a 1 in the central entry. That's the only non-zero entry in that column. And then in the third row, we have a 1 in this rightmost column. Again, since this is actually corresponding to just a generic matrix and not a system, we can continue moving further. So we'll continue on. We'll zero out the entries in this rightmost column. Notice that we're skipping the third column because the third column doesn't have a pivot in it. The pivots are the leftmost non-zero entry in each row. So I've got this 1, and then if I move to the second row, I've got this 1. If I move to the third row, my pivot is all the way over here in that fourth column. And so we're going to replace now row 2. So when we zero out above, we're going to kind of go backwards. We're going to zero out row 2 by taking the original row 2 and adding some scaled copy of row 3 to it. I'll zero out this 3 if I multiply the 1 by a -3. So I'm going to multiply that entire row by -3. I'm going to add the result to row 2, and I'll zero out that entry above. And now, last step, we'll zero out the entry in the top right. So we're going to replace row 1. Again, we're going to use row 3 to do it. We're always using that pivot entry to zero out our entries. That's going to make sure that we're preserving all of the zeros that we worked hard on earlier on in this process. And so in order to zero out this top right entry, I'm going to add -1 times row 3 to row 1 because -1 times 1 is -1. -1 plus 1 is what's going to give us our 0. And so we can evaluate that. And we end up now in reduced row echelon form. All right. So hopefully what I did kind of mimicked what your approach to those row reduction problems was. If you're having any questions still about the row reduction process, please do come see me and work with me. This is a process or a procedure that we're going to make heavy use of all semester long. So the work you put in now to make sure that you have a great understanding of that row reduction procedure, that's going to be time well spent for you moving forward. All right. So let's get into today's discussion. I think you're going to find a lot of the beginning of this video to be review. We've been talking about pivots and their impact on solutions and the shape of the solution space for a few class meetings now. But a review is good. And then towards the end of this discussion, we'll introduce a form that we can use to write our solutions to systems using. And that form is going to give us a lot of great insight as to the actual shape of that solution space, especially where we have infinitely many solutions to a system. So just some reminders and to explicitly highlight what we're up against today. We have been discussing augmented coefficient matrices and how they're connected to linear systems. We've seen that we can use the 3 permissible row reduction operations to obtain solutions to linear systems. We used all 3, actually we used 2 out of the 3 of those in the warm-up examples today. We didn't use a row swap, but we did use row scaling. We can multiply both sides of an equation by a non-zero scalar, not change the solutions. That's the same in the augmented coefficient matrix. We can multiply an entire row by a non-zero scalar and not change the solutions corresponding to the system that we're working on. And we can replace an equation or replace a row by that row plus a scaled copy of another row. And we made heavy use of that row operation in the example problems today and in all the example problems that we've done prior. We've talked about 2 reduced forms for our augmented matrices. The first form is row echelon form. It's this one where we have a staircase. These black squares are denoting our pivots. You'll notice that in this form, all of the entries below the pivots are zeros. The entries above the pivots, though, are allowed to be non-zero. We don't zero those out at this point. The advantage to row echelon form is that it tells us about the number of solutions that we have, and we'll highlight that explicitly today. But the locations of those pivots in particular are what indicate how many solutions we have, if we have any solutions at all, and if we should go forward and try to obtain the next form, which is reduced row echelon form. So row echelon form will tell you about the number of solutions that you have, but it will not tell you about those solutions. Like you have a bunch of work to do still in order to be able to find the solutions once you're in row echelon form. If you move to reduced row echelon form, then you can read those solutions directly off of this matrix. So this is a more convenient form. It's a little bit more work to get there, though. Changes from row echelon to reduced row echelon. Our pivots have to be 1s in reduced row echelon form. So we're going to make sure that the pivots take on a value of 1. And it's not only the case that the entries below the pivots have to take on values of 0, but the entries above the pivots also have to take on values of 0. So those pivots are the only non-zero entries in their columns. Everything else is zeros. And again, the advantage here is that you can read the solutions directly off of a matrix like this one. So we talked through pivots. Again, a reminder, the images that I'm showing you here don't really make this explicit, but the pivots don't necessarily have to occur along the diagonal, and it is not necessarily the case that every row or every column in your matrix is going to have a pivot. In fact, analyzing which rows and columns have pivots in them, in particular which columns have pivots in them, is going to be how we determine the number of solutions in our system. And also the roles of the variables in those solutions if we do have them. All right. So this is not the first time we saw pivots. We've seen them for about a week now. We've been working with them. But just a reminder, pivots are the leading non-zero entries in each row of a matrix once that matrix is in row echelon form. Leading just means the leftmost non-zero entry. A row in a matrix containing a pivot, just some terminology, we'll call that a pivot row. And similarly, a column containing a pivot is going to be called a pivot column. So we have, again, identified that the positions of these pivots determine the size of our solution space. The sort of checklist that we've gone down, this first one takes precedence over all of these others. If the rightmost column of an augmented coefficient matrix, so that augmented column beyond the vertical line that we're using, if that column is a pivot column, then we call that system inconsistent. It has no solutions. So if a system has no solutions, we'll call it inconsistent. If a system has solutions, whether it's one or infinitely many, we'll call it consistent. If all of the columns other than the rightmost column of the augmented coefficient matrix are pivot columns, so every column to the left of that vertical bar, if those are all pivot columns, then the system has a unique solution. There's only one. But if at least one column other than that rightmost column of the augmented coefficient matrix is not a pivot column, so if one of those variable columns is missing a pivot, then that system has infinitely many solutions, and we've called that corresponding variable a free variable, and we'll highlight that again today, and we'll make explicit really what we mean by that as well. So we'll take a look at 3 examples to sort of highlight the scenarios that we're seeing above. So in this case, actually let's start here in the middle. In this case, that rightmost column, the one beyond the augmenting line, has a pivot in it, and in that case, there are no solutions. The logic behind that is that this vertical bar is our equal sign in our system. It's taking the place of that. And so the left-hand side says I have 0 copies of x1, I have 0 copies of x2, so I have 0 on the left-hand side of this equation. And then 0 is equal to 1 is what this is saying. And 0 can't be equal to 1. That's a contradiction. And so because of that contradiction, there are no solutions to the system. Here in this left case, we've got a pivot in every column to the left of that augmenting column. So a pivot in the first column, pivot in the second column. That's going to mean that there's a unique solution. There are no free variables here. And then in the right example, we've got a pivot in the first column, but no pivot in the second column. There is no pivot also in the rightmost column. So I do have a free variable here. I do have solutions. And so there will be infinitely many solutions in that case. We can make a few fundamental observations about pivots based off of the size of an augmented coefficient matrix. There are really some limitations here. So if we're only interested in whether solutions exist or if they're unique, then we can leverage these ideas. In any m by n matrix, there can be at most 1 pivot per row. That's by definition, right? Because the pivot is the leftmost non-zero entry in each row. I can only have one leftmost non-zero entry. So the number of pivots is at most m in an m by n matrix. But similarly, in any m by n matrix, there can be at most 1 pivot per column, because if we're thinking about reduced row echelon form in particular, we're taking those pivots and we're zeroing out all of the entries above and below their locations. And so because of that, all of the entries aside from that 1 pivot entry are going to be zeros. So there can be no other first non-zero entry in that column. And so each column can have at most 1 pivot. And so the number of pivots has to also be at most n. So we can take the smaller of the 2 dimensions and identify that, hey, that's a limit on the number of pivots I can have. And so, for example, if I've got a 4x7 augmented coefficient matrix, and so the original coefficient matrix is 4x6, forgetting about that augmented column. The number of pivots in the augmented coefficient matrix at maximum is 4. I can have at most 1 per row and at most 1 per column. The row is the most limiting factor here. It's the smaller number. And so the maximum number of pivots is 4. And that means that either I'm going to have no solutions or I'm going to have infinitely many solutions. Having a unique solution here is not possible because I would need a pivot in every variable column to have a unique solution, and I have 6 variable columns, but the maximum number of pivots I can have is 4. And so that eliminates the possibility of having a unique solution immediately. but it is still possible to have no solutions, so to have an inconsistent system, or to have infinitely many solutions in this case. All right. So again, getting back into pivots and what they tell us about the number of solutions to a corresponding linear system, most of this is stuff that we've talked about already and highlighted already. I'm just collecting it here in one location for us. So we've said this a bunch. The locations of the pivots in a row echelon form matrix tell us about the number of solutions to the corresponding system. The pivots also tell us about the roles of the variables in the corresponding solution set. And we've mentioned that in an augmented coefficient matrix, all of the columns to the left of the augmenting line correspond to a variable in the system. And so here's a generic matrix or generic augmented matrix corresponding to a generic system with n variables and m equations. What I've added for us here is just an indicator at the top of each column saying, hey, this first column corresponds to x1, and the second column to x2, and the nth column to xn. So all of those columns to the left there are terms that correspond to variables. They're, the entries inside those columns are the coefficient attached to that variable. The rightmost column doesn't have any variables associated with it. That's the right-hand side of all of our equations in the system. Excuse me. All right. So if a variable corresponds to a pivot column, so basically if the column in the row echelon form of the augmented matrix has a pivot in it, then that corresponding variable is a basic variable. Basic variables have values that are determined, either directly determined or determined once the values of free variables have been chosen. If a variable does not correspond to a pivot column, then that variable is a free variable. And free variables can take on any value. And again, once all of the values for the free variables have been chosen, then the values of the basic variables are determined. So in some sense, the values of the basic variables are restricted. All right. Okay, so to recap what we've done here, the columns to the left of the augmenting line in an augmented coefficient matrix, they correspond to variables in the system. The pivots are the leftmost non-zero entries in each row. And rows and columns containing pivots are called pivot rows and pivot columns, respectively. If the rightmost column of an augmented coefficient matrix is a pivot column, then the corresponding linear system is inconsistent. It has no solutions. Again, remember, a pivot in the rightmost column means I have an equation that's essentially saying 0 is equal to some non-zero value, which is a contradiction. It can never be true. Otherwise, so as long as the rightmost column is not a pivot column, then the system is consistent. It either has a unique solution or it has infinitely many solutions. Remember, we can't have anything in between. Any variable in a system corresponding to a column which is not a pivot column in the augmented coefficient matrix is a free variable. Free variables can take on any value, and the system will remain consistent. The choices for the free variable's value, though, may influence the value that a basic variable must take on. All right. Any variable in a system corresponding to a pivot column in the augmented coefficient matrix is a basic variable. Basic variables are not free. Their values are completely determined once the values for any free variables have been chosen. One thing to maybe just mention and point out is that if I have multiple free variables in a system, those free variables are allowed to take on different values. They're truly free. It's not the case that all of the free variables have to take on the same value. Everything is completely free if we're a free variable. So free and flexible there. If a consistent system has at least one free variable, then it has infinitely many solutions. That's what we said where in the case that the rightmost column is not a pivot column. However, we have a column to the left of that augmenting line that is not a pivot column, then that corresponding variable is free. And as soon as I have a free variable, I have choice. I can allow that variable to take on any value I like, and because that variable can take on any value, there are automatically infinitely many solutions to your system. And then if a system has no free variables, then it has exactly one unique solution. So it's completely determined. I've got some examples for us to try, and I think we will try some of them. We'll use the row reduction applet as we go through and do it. So here I've got about 5 systems, I think, in their matrix form. We want to know, is the matrix in reduced row echelon form? Is it in row echelon form, or is it in neither? Once we've identified that, can we identify the locations of the pivots? And actually, these questions may be in opposite order of the way we'll answer them. We want to decide whether the corresponding linear system is consistent or inconsistent. We can do that. And for any consistent linear systems, we want to identify whether the system has any free variables. We want to be able to identify them. And then we want to identify the size of the solution space. And so let's see what we can do here. We'll start with system A. System A has no pivot in the rightmost column. It has a pivot in the third column, a pivot in the second column, and a pivot in the first column. Every column to the left of the augmenting line has a pivot associated with it. What I'm going to do with this one is I'm just going to write for us the solutions to these systems. So here's system A. Reading across the top row, remember each column is a variable. So this says I have one copy of x1. I have no copies of x2 and no copies of x3. And so I have one copy of x1, and that takes on a value of 2. You can look at the right-hand side over here and ignore kind of what I'm typing. So I've got x1 is equal to 2. And then similarly in the second row, no copies of x1, one copy of x2. So x2, no copies of x3 is equal to -1. And so we've got x1 equals 2, x2 equals -1, and then similarly, this last row is telling us that x3 equals 3. And so we see the solutions to the first system, or to the system corresponding to that first augmented coefficient matrix, are x1 is 2, x2 is -1, and x3 is 3. All right, I'm going to open up a new text cell, and we'll do the same thing here. In system B, we've got, actually I'm going to bring this back. In system B, we've got no pivot in the rightmost column. So immediately we can identify that this system is consistent. If we're looking at the columns to the left of the augmenting line, I've got a pivot in the first column, zeros below it. That's good. I've got a pivot in the second column, zeros below it. No zeros above it though, so that 2 is preventing me from being in reduced row echelon form. I'm not in reduced row echelon form, but I am in row echelon form because for the 2 pivots that I have, the entries below those pivots are taking on values of 0. There is no pivot in this thirdmost column. That third row is a row of all zeros. And so as it stands now, we have solutions. There's no pivot in that rightmost column. There is a column to the left of the augmenting line that is missing a pivot. That's the third column. And so that third column corresponds to a free variable. As soon as we have a free variable, we have infinitely many solutions. As it stands right now, though, because we're in just row echelon form and not reduced row echelon form, we have a bit of a hard time reading the solutions off of this matrix. So I'm going to go back to our row reduction applet. I'm going to fill in this matrix, and then we're going to use the applet to reduce the, I'm going to reset. We're going to use the applet to reduce the matrix to reduced row echelon form so that we can have an easier time reading the solutions off of it. So that last row is all zeros. So this matrix is actually close to being in reduced row echelon form. The only entry that we need to remove or to zero out is this 2 that's in the top center. We'll replace row 1 then, because row 1 is the location of the entry that we want to change. We're going to use the pivot to remove it. So I'm going to pay attention to this 1 and this 2 that I want to remove. If I want to remove this, I can scale the second row by a non-zero scalar and add it to the first row. If I scale that second row by -2, -2 times 1 is -2, and -2 plus 2 is going to give me the 0. Remember, I can't just scale a single entry. I've got to scale the entire row when I do this. So basically, I'm going to add 0, then -2, then -8, and then 10 to row 1 as I do this operation. And let's see, oops, not row 3, row 2. Okay, so now we've got our matrix in reduced row echelon form. What I'm going to do is I'm going to move this tab over here so that we can type out the solution. Right now, that top row is saying that 1x1 plus -9x3 equals 7. And it's also saying that, so I'm going to put this down below. I'm actually going to center these maybe. The second row then is saying that 1x2 plus 4x3, so I'm getting 4x3 from here, it's in the third column, is equal to -2. And so there are the solutions to my system. This is hard to read off of and to grasp what those solutions might look like. I think we're going to get a better way in a bit, but we could also rewrite this with the basic variables on the left-hand side of the equal sign and the free variable on the right-hand side. And in doing that, we'd have instead x1 is equal to 7 plus 9x3. So I'm adding that 9x3 to both sides. And then x2 is equal to -2, and then I'm going to subtract that 4x3 from both sides, so minus 4x3. And I think this, in fact, maybe I can get rid of these and box this up. This form for the solutions, sorry about that, this form is a little bit better because now I can tell that x1 and x2 are basic variables whose values are going to be determined by choice of the free variable x3. So if I let x3 be 0, then x1 takes on a value of 7 and x2 takes on a value of -2. If I let x3 be, let's say 5, then I am going to get different values for x1 and x2. All right, so let's bring this back. I think maybe I just want to do one more, but if we take a look just quickly at C, then we'll do D, and we'll leave E alone. We'll actually comment on C and E quickly, I think. C, if you just do a row swap, then you're in reduced row echelon form, and you have a pivot in both of the variable columns. So there should be a unique solution here saying that x1 is 3 and x2 is 2. In this in E, I have a scenario where it's got to be either the case that I have no solutions or infinitely many solutions, because I'm limited in the number of pivots I can have. I have only 2 rows, so at most I can have 2 pivots here. But I've got 1, 2, 3, 4 variables. And so at most I can have 2 basic variables and I'd be left with 2 free variables. It could be the case that I end up with an inconsistent system here, but the form of the matrix is enough to eliminate that as well. I've got a pivot here in the top left entry, zeros below it, and a pivot here in the second entry of the second row. So I can tell that there's not going to be a pivot in this rightmost column. This will be a consistent system, and because of the limitations with the pivots, I'm going to have infinitely many solutions because there are guaranteed free variables now. Let's take a quick look at D. So I'm going to reset the row reduction applet. Right now, D is not in either row echelon form or in reduced row echelon form. I don't have that staircase format. I've got this pivot in the top left, but there aren't zeros everywhere below it. And so in order to tell whether we've got solutions, I'm going to have to pursue row echelon form at least. And then once we know that we have solutions, if we do have them, then we can pursue reduced row echelon form if we like. So right now, the 1 in the top left is great. The 0 in the second entry in the first column is also great. We want to zero out this bottom entry. And so we're going to replace row 3 because that's where that entry that we want to zero out is. And we're going to replace it using the pivot. The pivot is in row 1, so we're going to use row 1 to do it, and we're going to multiply row 1 by -1, so that when I add -1 and +1, I get 0. All right. And now our first column is done. We can move to our second column. We've got a 1 in the pivot position here in this middle. That's great. We like having the 1 there. And we can pursue row echelon form by zeroing out the entry below that 1. So again, we're going to replace row 3. We're going to use the pivot to do it. So we're going to use row 2 because that's the location of the pivot in this column where I want to eliminate that value, or zero out that value rather. And the right scalar to choose here is again -1. And so we can run that row replacement operation, and now we have the row echelon form for this matrix. And if we look at the pivots, I've got a pivot in this top left entry, I've got a pivot in the second row in the second column, and if I look at the third row, now I have a pivot, but it's way over in this rightmost column. It's in the augmented column. And so this is indicating to us that 0 on the left-hand side is equal to 5 on the right-hand side, and we know that that can't happen. This is an inconsistent system. There are no solutions there. All right. Thank you for taking the time to walk through those examples with me. I hope that's helpful as we think about the row reduction process, row echelon form, reduced row echelon form, pivots, and how they impact our solutions, and then also reading solutions off of an augmented matrix that's in reduced row echelon form. So now I want to take a look back at something that we had encountered earlier. So in the system corresponding to matrix B, we ended up with free variables, and we saw that we had solutions that we could describe in terms of that free variable x3. But this still doesn't give us great insight as to what that solution space looks like. We know that we have infinitely many solutions, and we know that we can choose any value for x3. But what does that mean? What is the collection of solutions organized as? And we'll take a look at that here with an example, and then we'll return to this one, and we can rewrite this example using what we'll call parametric vector form, which is going to give us insight into the geometry of the solution space. So before we can get into parametric vector form, we've got to talk a little bit about matrix equations and how they're equivalent to linear systems. We're going to see in linear algebra that lots of different forms of equations in different environments can be made equivalent to one another. So we've seen that we can convert a linear system into an augmented coefficient matrix, but that really converts the linear system into a matrix equation like this one, where I've got a matrix A times a vector x is equal to some new vector b, which we're going to solve instead. And that's actually what we've been doing by row reducing the augmented coefficient matrix. The solution to a matrix equation, though, is a vector. Right? I'm taking the matrix A, I'm multiplying it by a vector x, and I'm getting back a vector b. And I want to know what the original vector x that I multiplied by A had to be in order to arrive at that resulting vector. So for example, the linear system here, x1 minus 2x2 plus x3 equals negative 5, and 2x2 plus 3x3 equals 9, corresponds to this matrix equation. So we're just rewriting this a little bit different than we have been previously. Previously, we would kind of erase this vector and then just smash the matrix and the vector on the right-hand side together, seeing that we'd have 1, negative 2, 1, augmented by negative 5, and then 0, 2, 3, augmented by 9. We're now just writing this in a different form. And it gives us some interesting insights too, because we're taking a three-dimensional vector, we're multiplying it by a matrix, and we're getting back a two-dimensional vector. So we're starting to see some insight into how matrices change vectors. So there's an example of converting a small system into a matrix equation. Here's a generic example. So if I have some general linear system that has m equations and n variables, I can rewrite this as a matrix equation where I just have that coefficient matrix that we had talked about previously before talking about the augmented coefficient matrix. But that coefficient matrix times the vector x is equal to that constant vector b. And now we're trying to solve this matrix equation. When a linear system has a solution with free variables, the solution vector to the matrix equation here won't be completely determined. It's going to have free variables associated with it. Free variables are going to show up here, though, as parameters inside of the solution vector. They're going to be quantities that we're going to say, hey, this is a placeholder. It can change. It can take on any value we'd like it to take on. And once we parameterize the solution vector, we can express that solution vector as a sum of a constant vector and one or more directional vectors that are scaled by parameters. And those parameters are going to show up, those free variables are going to show up as the parameters. The process of doing all of this is called writing the solution in parametric vector form. We'll see exactly how to do that, though. So here's an example. I'm giving you a matrix to start with. So we have this augmented coefficient matrix. It is the one that corresponds to this system here, I think. Yeah, it looks like that one. And I'm telling you that this augmented coefficient matrix has this particular reduced row echelon form. So we've done some row reduction here to obtain the form of this vector. What we've seen previously is that we can read the solutions off of this reduced row echelon form. We can see that x1 and x2 are basic variables because they correspond to our pivot columns. x3 is a free variable because it's got no pivot in that column. The values of x1 and x2 both depend on the value that free variable takes on. And so what we can see here is, again, the top row of this reduced row echelon form matrix says that x1 plus 4x3 is equal to 4. We can rewrite that by subtracting 4x3 from both sides, and we get x1 is equal to 4 minus 4x3. And then similarly, we can read the solution to the second equation off. We'd have x2 plus 3 halves x3 is equal to 9 halves. But then similarly, we can solve this for x2 by subtracting 3 halves x3 from both sides. And we obtain this here, that x2 is equal to 9 halves minus 3 halves x3. And then, because the solution vector we know is going to be this three-dimensional vector, right? We have to start with 3 components. I'm going to have an x1 component, an x2 component, and an x3 component. The value of the x3 component is free. It's just whatever we've chosen x3 to be. And so here is the solution vector. This does, though, mask the solution space. It's kind of the same thing that we did here with our earlier example. We just didn't explicitly write the third component, that free component. This does, though, again, mask the structure of the solution space. But if we decompose the vector into a constant vector plus a directional vector, with respect to that parameter, so here the free variable x3, that's going to provide us with additional insight. So here's what that looks like. We know that the solution vector x is going to have 3 components, x1, x2, and x3. We also know that x1 is 4 minus 4x3 by reading off that top row of the augmented matrix in reduced row echelon form. And that x2 is here, 9 halves minus 3 halves x3, again, for the same reason, reading that solution off from the second row. And that x3 is still free. It's not bounded by anything. And so we just list that x3 is whatever we want it to be, x3. From there, we can decompose. So we can decompose into a constant vector. So the constants in this first component is 4. In the second component, it's 9 halves. Neither of those is attached to a variable or to a parameter. And in this third component, my constant isn't listed, but it's 0. I have nothing plus x3. And so my constant vector is going to be 4, 9 halves, 0. And then I'm going to add to that the component that corresponds to x3. So I'm going to have negative 4x3, then negative 3 halves x3, and then x3. You'll notice now, though, that all of these entries have an x3 in them. And x3 is just a number. It's a scalar. And so I can factor out that scalar, and we can have now 4, 9 halves, 0 as some constant vector. And then plus, this is a directional vector, negative 4, negative 3 halves, 1, times some scalar. And so if I start at a point, and I have some direction or some slope, you might have called it in 2 dimensions, times a scalar, that's a line. So the solution space here consists of all vectors of this form going through this point and moving in this direction from that point. It is a line, and there it is. So there's my base point, 4, 9 halves, 0. And then a directional vector, negative 4, negative 3 halves, 1. So all of the points along this blue line are solutions to that system that we started with. That system was this one. So an entire line of points satisfies that system. What I'd like to do is I'd like to just return quickly to the example that we had done over here, where we can just decompose this one into parametric vector form. I'm going to make this a little bit bigger. Again, pay attention over here on the right-hand side, but solution in parametric vector form. And so our vector x is going to have 3 components again. And that was because our original system had 3 variables in it. The augmented coefficient matrix had 3 columns to the left of the augmenting line and then the constant column to the right. We're saying that B matrix, we can write the x1 component we said was 7 plus 9x3. And the x2 component is negative 2 minus 4x3. And then, because we need to have 3 components here, the third component, x3, was our free variable. So x3 is free. And now we can break this apart into a constant vector. So the constant term in the first entry is 7, and then negative 2 in the second entry. And then again, we've got 0 in that third entry. And so this is going to be equal to the vector 7, negative 2, 0, plus the variable terms, the terms corresponding to our free variable. So we're going to have 9x3, negative 4x3, and x3. So there we are. We have our constant vector. This is our point. And now we have our vector that's parametrized. This has x3s in all of the components, so we can remove out the x3. We can factor it out. I'm going to cheat a little bit and copy paste. And what's changing here is that we're getting rid of the x3s in that second vector. We're factoring it out. We've got to remember that when we factor out the x3 from the bottom component, that is really x3 times 1. And oops, I didn't have an equal sign. So, and this is the nice form that we want, so let's box it up. I think, yeah. And so there's the solution. The solution to the augmented coefficient matrix, to that system that we saw earlier, is a line. It passes through the point 7, negative 2, 0 in space. And then it consists of all the points in the direction of 9, negative 4, 1 from that point. Which is really nice. Like, we get some really good insight about the shape of the solution space here. So to recap on free variables and the geometry of solution spaces, we only saw scenarios here today where we had one free variable. It was x3 in both cases, but it could be the case that a different variable is free or that we have multiple free variables. The strategy for decomposing the solution vector is the same. We have a constant vector, and then we have a new vector for each free variable. So we're just going to decompose it into the pieces corresponding to constant and then each variable. Each free variable corresponds to a directional vector that the solutions can travel along. And so a solution space for a system with no free variables at all is a single point. I have a point and I can go nowhere. The solution space for a system with exactly one free variable is a line. I have a point and I have a direction that I can travel in. And remember that scaling a vector by a positive number travels in its direction, but scaling a vector by a negative number travels in the direction exactly opposite of that vector. And so that does really trace out a full line. The solution space for a system with exactly two variables is a plane, because I can travel in any combination of those two directions away from that point. And a solution space for a system with three or more free variables is a hyperplane. Hyperplanes we can't visualize, but it's a higher dimensional space. I've got some examples here at the end of this slide deck for you to try. I hope you will come back and try them. Try writing out the solution of the system in parametric vector form and describe the geometry of the solution space. I'll click through them in the video just so that you can see what the examples are. So I have this 3x3 system. I have another 2x3 system. In this one, you're guaranteed to either have no solutions or to have at least one free variable here because you've got only 2 equations and 3 variables. Here, you've got a system of 4 equations and 3 variables only. So think about the impact that the the restriction of the number of pivots may have on that scenario. Here you've got a system of 3 equations and 2 variables, 2 equations and 4 variables. And so I hope you'll try at least some of those. It's great to get practice with the row reduction procedure, reading solutions off of a reduced row echelon form matrix, and to get more practice with writing solutions in their parametric vector form. All right, that's it for this video. For homework, you can start homework 3 after watching this video on MyOpenMath. You're ready to do that. And then next time, we'll do a row reduction workshop, and you'll have your first attempt at the row reduction gateway exam. Thanks, everybody.